Welcome to this explainer. Today, we are going to completely demystify machine learning by tracking the full end-to-end life cycle of how a model is actually built. We're going to break down all the fundamental terms and definitions so you can see exactly how we go from a pile of raw data to real-world impactful decisions. And honestly, understanding this foundation is absolutely crucial. It's really the only way to genuinely trust the decisions these models are making in our everyday lives. Because let's face it, if you don't know how this system is built under the hood, it's pretty tough to know if you should trust what it spits out. So let's unpack the whole shebang. Okay, before we build anything, let's establish our baseline. Machine learning is fundamentally a massive paradigm shift in computing. Instead of humans hard-coding strict, rigid rules for a computer to follow, like a traditional software program running endless if-then statements, we train a model from input data. We're essentially giving the system a huge stack of information and just letting it figure out the patterns on its own. That way, it can make useful predictions on completely new, never-before-seen data. It's kind of like the difference between giving a computer a pre-drawn map versus teaching it how to navigate the wilderness entirely on its own. So instead of thus reading you a dry textbook dictionary, we've synthesized these dense concepts into a logical 5-step journey. We'll hit the data building blocks, move into architecting the model, tackle the training process, look at evaluating success, and finally wrap up with common pitfalls and biases. All right, let's jump right into Section 1, the data building blocks, which is really the absolute foundation of every single machine learning system out there. When we talk about data in ML, we're usually dealing with what we call examples. And these basically come in 2 distinct flavors. First, we have your labeled examples. Think of these as the teaching tools. They contain the features plus the ground truth answer, or what we call the label. This teaches the model what a correct outcome actually looks like. Second, we have unlabeled examples. These contain the features only. We use these later on when we want our trained model to make a prediction in the real world, a process we call inference. Let's look at how these pieces fit together. You've got your input features, say things like temperature, humidity, and barometric pressure. And these lead directly to our label. In this specific scenario, the label is a student test score that we actually want to predict based on those weather features. So the label is simply the specific answer we want the machine to learn to figure out, using those features as its clues. Now, it's really important to remember that data comes in all sorts of different shapes, right? To do our feature engineering properly, we have to carefully separate our categorical data, which are discrete buckets like traffic light colors, red, yellow, green, from our continuous features, which are infinite floating point numbers, like those temperature readings we just mentioned. This distinction is absolutely critical. Just think about it. If a model mathematically thinks the color red is somehow greater than the color green just because of how we lazily encoded the data, well, the whole logic falls apart. Treating these types correctly is essential for the model to grasp the true mathematical relationships. Okay, now that we've got our data sorted out, let's move right into Section 2 and see how this builds into the actual architecture where the machine learning magic happens. The absolute beating heart of modern AI architecture is the neural network. At its core, it's a model containing at least one hidden layer that can mimic extremely complex, nonlinear relationships between your features and your labels. Look, if you only had a simple linear relationship, a basic straight-line graph would do the trick just fine. But real-world data is messy, it's interconnected, and it's highly unpredictable. Neural networks are specifically designed to capture the intricate, curving, wild patterns that a straight line could just never handle. If we zoom in a bit, inside these networks are individual nodes, or neurons. And every single neuron executes a simple but incredibly powerful 2-step action. First, it calculates a weighted sum of the input values. It's literally multiplying the inputs by their assigned weights. Second, it passes that sum to an activation function, like a ReLU or a Sigmoid function. And that activation function? That's what introduces the crucial nonlinearity we were just talking about. It basically acts as a gatekeeper, deciding exactly what signals get to move forward through the network. Now, a massive point of confusion for beginners and something you really need to nail down is the difference between parameters and hyperparameters. Parameters are the internal weights and biases that the machine literally learns and adjusts on its own during training. You don't touch these. Hyperparameters, on the other hand, are the external dials that you, the human engineer, control before the training even begins. Things like setting the learning rate or choosing the number of hidden layers. Simply put, you build the overarching structure, the machine fills in the weights. All right, we've got our ingredients, we've designed our architecture. Let's jump into Section 3, the active cooking phase, the training process. Which brings us to the million-dollar question. We know a model takes inputs and spits out predictions, but how does it actually learn from its errors over time? How does it literally get smarter? Well, it does this through cycles. The model goes through multiple epochs, which are basically full training passes over your entire data set, and those are usually broken down into smaller chunks called mini-batches. During these iterations, the model uses a brilliant mathematical technique called gradient descent. Gradient descent iteratively adjusts those learned weights to minimize the model's loss. And loss is just a fancy way of measuring how far off the model's prediction is from the actual truth. Think of gradient descent like being blindfolded on a really rugged, uneven hill. You feel around with your feet trying to find the steepest slope downward, taking step after step, iteration after iteration, until you finally reach the lowest point of error down in the valley. The lower the loss, the better the model. But wait, how do we keep the model in check? Because if a model just blindly memorizes the training data, it is going to fail miserably on new data. That's a huge problem called overfitting. To prevent this, we use L1 and L2 regularization. L1 penalizes the absolute value of the weights, which actually drives irrelevant feature weights to exactly 0, effectively pruning them out completely. L2, meanwhile, penalizes the squared value, which drives extreme outlier weights very close to 0 without entirely eliminating them. Both methods act like speed governors on a sports car, ensuring our model stays adaptable and doesn't just memorize the test answers. Okay, so once our model is trained and properly regularized, we absolutely must evaluate its performance. Section 4 is all about seeing if it can successfully generalize to the wild, unseen data of the real world. Let's look at a seemingly amazing metric. Imagine you build a model to predict the weather in a warm subtropical city, and it achieves 99.93% accuracy. No way, right? Does this mean we've built a flawless genius model? Well, actually no. This reveals the complete illusion of a class imbalance dataset. Because it only snows, say, 25 days a century in the subtropical city, the model just got lazy. It just guessed no snow every single day. So sure, it racked up nearly 36,500 true negatives, which artificially pumped that accuracy up to 99.93%. But it had 0 true positives. It missed every single actual snowstorm. It has literally 0 real predictive power. And this subtropical snow trap is exactly why we have to choose our evaluation metrics carefully, based entirely on our specific task. You need to know, are you doing classification, predicting discrete categories like snow versus no snow, or are you doing regression, predicting a continuous floating point number like a house price? Relying on raw accuracy for a highly imbalanced classification task is a massive, massive pitfall. I mean, think about medical diagnoses or fraud detection. If a disease is incredibly rare, a model could be 99% accurate just by guessing healthy every single time. That would be absolutely disastrous in the real world. Speaking of disasters, let's move into our 5th and final section, common pitfalls and biases. Let's explore what happens when these pristine mathematical equations collide with messy human reality. So one major mechanical issue, as we touched on a minute ago, is overfitting. And we have a great trick for this. Much like a chef pulling a delicate pastry from the oven right before it burns, we use a technique called early stopping. We intentionally halt the training process before the training loss finishes decreasing, literally the very second we see its performance on a separate validation dataset start to get worse. This stops the model from overfitting to the training data, protecting its precious ability to generalize. But honestly, the most critical pitfall of all involves the human biases that creep into our systems. If the data we feed a model contains stereotyping, prejudice, or just systematic errors in how the samples were collected, the model doesn't know any better. It will simply learn, absorb, and repeat those exact flaws. The machine has no inherent moral compass. It doesn't know what's fair. It only knows its data. So if we aren't incredibly vigilant about our ML fundamentals, we end up creating automated systems that just scale human prejudice rather than fixing it. So I want to leave you with a final, really provocative thought regarding these feedback loops. In machine learning, a model's predictions often dictate the very environment it operates in. Think about it. If an algorithm's recommendations dictate what content humans see today, and then those human reactions generate tomorrow's training data, how on earth do we break that loop? As these models increasingly shape our global society, how do we guarantee the data they learn from tomorrow remains balanced, fair, and truly representative of the world we want? It's a massive structural challenge for sure. Thank you so much for joining me on this explainer, and hey, always remember to keep questioning your data.